By year-end 1964, 3,600 NASA and 1,400 contractor personnel were employed in over 400 project and support offices at the Manned Spacecraft Center's Clear Lake facility. Additional office and laboratory space was nearing completion in the Vibration and Acoustical Test Facility, the Mission Simulation and Training Facility, and in an addition to the Spacecraft Research Building. The office and medical wing of the Flight Acceleration Facility was completed in December, while equipment emplacement continued in the adjoining centrifuge laboratory. In the Space Environmental Simulation Building, steelwork was 98% complete on improvements to the 120-foot high space simulation chamber. Reinforcing ribs were added to the sidewalls, and a 2-inch thick stainless steel shell was added around the door. In the Houston Mission Control Center, all major equipment was installed and in the final stages of acceptance testing. Control consoles and displays in the 2 mission control rooms were undergoing subsystems testing as seen in the 3rd floor control room area. In the real-time computer complex, the 4 IBM 7094 computers were operational. The facility will assist in providing real-time decision capability for vehicle systems and trajectory analysis. During the last half of 1964, MSC continued to direct the efforts of a vast government industry team in pursuing manned spacecraft program objectives. In R&D programs, such devices as this air-bearing Beta trainer were introduced. Beta, for Balanced Extravehicular Training Aircraft, will be used to study the problems of movement and tool handling in free space. It can duplicate the inertial forces acting on the operator while eliminating the frictional forces he experiences on Earth. The unit cylindrical plenum chamber creates 2 nearly frictionless air-bearing surfaces, one between the dished platform and itself, the other between the plenum chamber and the floor. At nearby Ellington Air Force Base, MSC conducted a landing attenuation rocket test using a Gemini boilerplate. 2 12,000-pound thrust rockets supply the reaction force. Ignition is triggered by an impact switch suspended from a 10-foot cable. The rocket successfully slowed the boilerplate's descent from 27 feet per second to approximately 9 feet per second. The first full-scale drop test using the landing rockets and a developmental parasail system was conducted in October over Trinity Bay near Houston. Both the parasail and rocket landing systems are MSC research and development programs being considered for possible manned spacecraft application. All test sequences occurred on schedule. In the area of flight crew training, the 3rd class of astronauts continued to receive survival instruction, including training at the Navy's Water Survival School, Pensacola, Florida, and in the desert near Stead Air Force Base, Nevada. The latest group of astronauts also trained with Gemini personal parachutes at Ellington Air Force Base. The parachutes would be used during a mission abort requiring astronaut ejection from the spacecraft. The flight crews for the 2nd Manned Gemini mission, or GT-4 flight, were announced in July. The prime crew will be James McDivitt and Edward White. The backup crew will be Frank Borman and James Lovell. The GT-4 crew members began intensive Gemini flight preparation, including weightlessness training, in a Gemini cabin mock-up carried aboard an Air Force KC-135 aircraft. Gemini flight crew training in the centrifuge at the Naval Air Development Center, Johnsville, Pennsylvania, was accomplished in November. The center placed a new gondola in service, which can be fitted with specific test packages, including an active Gemini instrument and control assembly. NASA's Ames Research Center, Moffett Field, California, made their centrifuge facilities available for additional Gemini flight crew training. The equipment can introduce vibration forces in addition to those of high gravity. GT-4 crews also began flight indoctrination in the Gemini mission simulator at Houston. The simulator was delivered by McDonnell Aircraft in July. It will be linked with the Houston Mission Control Center to facilitate the training of mission controllers. GT-3 crews, meanwhile, continued training in the second Gemini mission simulator at Cape Kennedy. The simulator's cabin arrangement duplicates that of Spacecraft 3, which will be flown on the first manned Gemini mission. Astronauts participated in post-landing sea qualification tests of Gemini Static Article 5 in the Gulf of Mexico. Static Article 5 duplicated the weight, center of gravity, and configuration of Spacecraft 3. Stability, seaworthiness, and post-landing operation of key systems were tested. Information on human physiological reactions to a long-duration sea environment in the Gemini spacecraft was also obtained. Static Article 5 was the first production spacecraft to complete a qualification testing program at the Manned Spacecraft Center. Additional water tests included egress training from a boilerplate spacecraft in a freshwater tank at Ellington Air Force Base. The tests were designed to establish confidence levels that will aid the astronauts in handling any post-landing emergency. The Gemini spacesuit began acceptance testing both at the Army's Quartermaster Research and Engineering Laboratory, Natick, Massachusetts, and at the Manned Spacecraft Center. In a wear comfort test, a space-suited subject spent 96 hours in the center's 8-foot diameter pressure chamber. The cabin and suit were maintained at the 100% oxygen environment and pressure that will be used during spaceflight. The suit met all wear test requirements. Astronaut Russell Schweikert was the subject of a biomedical sensor test. Purpose of the test was to determine how well the tiny sensing devices could be worn while attached to the body for long periods of time. The astronaut donned his Gemini spacesuit on October 19th. He then began a number of tasks simulating actual wear performance. The suit was removed 8 days later. The test showed that the sensors could be worn for extended periods of time without irritating the skin. In the Apollo spacesuit program, the latest experimental pressure suit was received from the prime contractor, Hamilton Standard, Windsor Locks, Connecticut. The garment contains features that are being evaluated for use in the prototype lunar mission suit. An experimental meteoroid protection garment was designed and fabricated by MSC's Crew Systems Division. The suit satisfies a high meteoroid flux protection requirement. Efforts are also underway to produce a fabric armored suit. The handling and use of scientific equipment and walking devices was evaluated in terrain of volcanic origin near Bend, Oregon. Test subjects wore an interim Apollo pressure suit, a portable life support system, and a thermal overgarment. The studies indicated that necessary lunar tasks could be performed by a spacesuited astronaut. Although MSC has the overall responsibility for manned spacecraft programs, it depends on other NASA centers for information and services that will aid the accomplishment of these programs. An example is the use MSC is making of the Ranger spacecraft program administered by NASA's Jet Propulsion Laboratory, Pasadena, California. Photographs transmitted during Ranger 7's approach to the lunar surface on July 31st showed that expected hazards such as fissures, furrows, and boulders did not appear to be present. The photographs increased confidence in the Apollo spacecraft design. While additional lunar reconnaissance will be needed before a manned landing can be attempted, much of this information will be obtained by unmanned surveyor spacecraft, also the responsibility of the Jet Propulsion Laboratory. The first flight article surveyor is shown in systems testing. It is scheduled for flight testing before the end of 1965. The surveyor, shown in a scale model, will land on the moon, analyze its surface and environment, and radio its findings back to Earth. Other programs that have aided the manned spacecraft effort have been conducted at NASA's Langley Research Center, Hampton, Virginia. In one of over a dozen basic research projects, the center tested fuel sloshing characteristics of a 1/6 scale LEM fuel tank. Vibration frequencies were introduced similar to those that will be encountered during LEM engine firings. Langley also converted its moving base docking simulator to a lunar excursion module configuration. A pilot flies the simulation from the crew station of the simulated LEM. He lies on his back and aims the spacecraft through the overhead docking window. The device is for simulation purposes and does not represent the actual LEM configuration. The docking simulator is being used to evaluate command and control modes, vision, and visual docking aids. Future MSC support will come from spacecraft launch preparation facilities nearing completion at Cape Kennedy's Merritt Island launch area. The operations and checkout building achieved beneficial occupancy in September. MSC turned over control of the O&C complex at Mila to the Kennedy Space Center on January 1st, 1965. Events in the Gemini program led to the erection of Gemini Launch Vehicle number 2 at Cape Kennedy in mid-August. Subsequent vehicle checkout was delayed by damage from an electrical storm and by work stoppages imposed by hurricanes which approached the Cape in August and September. Payload for the launch vehicle was Spacecraft 2, which arrived at the Cape in early October. It was the first spacecraft to go through the Mila checkout facility. Following pre-mating inspections and checkout in the White Room at Launch Complex 19, the spacecraft and vehicle were joined. Countdown 0, December 9th. The vehicle's first stage engines ignited, burned for almost 2 seconds, and shut down. Loss of pressure in the booster hydraulic system resulted in automatic shutdown. The booster hydraulic system was modified, and the flight test was successfully conducted in January 1965. At the McDonnell plant in St. Louis, Gemini production status was reflected in a series of manned altitude tests conducted on Spacecraft 3. GT-3 flight crews participated. The tests validated the environmental control system and simulated the duration and altitude of the spacecraft's forthcoming manned orbital flight. They were one of the last major series of tests performed on the spacecraft prior to its acceptance in late December. During the same period, the cabin for Spacecraft 4 entered systems testing. Sequential, electrical, and instrumentation systems tests were performed. Spacecraft 5 through 10 were in earlier stages of assembly and test. Other McDonnell efforts led to a simulated flight test of the first Agena docking adapter ring. A transponder mounted on the extendable boom will aid radar acquisition of the Agena target vehicle by the Gemini spacecraft. The adapter ring met all performance criteria. In November, it was shipped to Lockheed for mating with the Agena vehicle. Gemini qualification testing was reflected in continued ejection seat tests at China Lake, California. Instrumented dummies were placed in a boilerplate spacecraft mounted on a rocket-powered sled. When the sled reached a speed imposing maximum aerodynamic pressure, the escape system was actuated. The last of 4 ejection seat qualification tests using the rocket sled were conducted in December. A ground-level test of the Gemini ejection seat mounted in an F-106 aircraft was conducted at El Centro, California. The test successfully laid the groundwork for future altitude ejection tests in which the aircraft will fly at speeds approaching Mach 2. In December, the Gemini Rendezvous radar, manufactured by Westinghouse at Baltimore, passed a certification and performance evaluation at the White Sands Missile Range, New Mexico. A transponder carried in a T-33 aircraft simulated target vehicle signals. In December, the computer for Spacecraft 5 entered acceptance testing at IBM's Owego, New York plant. Computers for the first 3 Gemini spacecraft had already been delivered. Also in December, the Gemini re-entry control system was subjected to its first hot firing system qualification test at Rocketdyne's Santa Susana Field Laboratory. It met all test objectives. Keeping pace with spacecraft development were the manufacturing and testing of the Gemini launch vehicles. Following GLV-3 acceptance in October, the Martin Company erected GLV-4 in the Baltimore Vertical Test Facility. The vehicle passed its acceptance tests in early December. At the Lockheed Missiles and Space Company, Sunnyvale, California, the first Gemini Agena target vehicle underwent preliminary systems testing. By the end of December, it had been delivered to Lockheed's Santa Cruz test base for the beginning of hot firing tests. The launch vehicle for the first Agena was erected at Cape Kennedy's Launch Complex 14. The vehicle is an Atlas SLV-3 manufactured by General Dynamics Astronautics, San Diego. It will be used to check out ground equipment and launch facilities prior to its use in the GT-6 flight, the first Gemini rendezvous mission. In the Apollo program, increasing amounts of flight hardware entered full-scale testing programs. At Cape Kennedy's Launch Complex 37B, Apollo Boilerplate 15 was readied for a flight test with a Saturn I SA-7 launch vehicle. Saturn development is directed by NASA's Marshall Space Flight Center, Huntsville, Alabama. Flight objectives included checking launch vehicle and spacecraft compatibility, effects of aerodynamic loads on the spacecraft during boost flight, and jettisoning of the launch escape tower using the escape motor instead of the jettison motor. Launch occurred on September 18th. Boilerplate 15, together with the Saturn I second stage, went into a low Earth orbit from which no recovery was planned. All mission objectives were satisfied. The test provided data that will help ensure the spacecraft's performance aboard the first Saturn 1B flight, a highly important mission which will verify an all systems up vehicle spacecraft testing concept. On December 8th at the White Sands Missile Range, a Little Joe 2 vehicle launched Boilerplate 23 in continued testing of the Apollo rocket escape subsystem under launch abort conditions. At 31,000 feet, a signal from the ground directed the vehicle to execute a slight pitch-up maneuver, initiating the abort sequence. The pitch-up maneuver imposed the highest aerodynamic and internal structural loads anticipated for Apollo. After burnout of the launch escape motor, canards on the escape subsystem opened and oriented the craft blunt end forward. Tower jettison removed the forward heat shield, uncovering the parachute bays. The dual drogue parachutes successfully reduced command module oscillations, permitting scheduled deployment of the pilot and main parachutes. All mission objectives were met. The test paved the way for more severe tests designed to qualify the spacecraft for any launch abort emergency. At the Downey, California plant of North American Aviation, hard mock-ups of the Apollo Block II lunar mission spacecraft were approved in a design engineering inspection held in October. Unlike early Apollo spacecraft, Block II modules will carry rendezvous radar and docking devices. By the end of December, Command and Service Modules 009 had completed structural assembly and were in systems installation. The 009 modules are the first flight articles of the Block I spacecraft series. They are scheduled for an unmanned Earth orbital launch aboard the first Saturn 1B in early 1966. During November, North American completed the installation of Boilerplate 14. The spacecraft will be known as House Spacecraft Number 1 and will be maintained as a permanent development fixture for testing systems installations and perfecting integrated systems capability. Boilerplate 14 became the first spacecraft to complete acceptance testing by the first operational acceptance checkout equipment station. The test complex is the first of 12 such stations being built by General Electric, Daytona Beach, Florida, for installation at NASA and contractor sites. Other checkout equipment became operational at North American, including a tilt table polarity checker. The device is designed for testing guidance and navigation equipment. Development tests continued at Downey to perfect the design of the command module's aft heat shield structure. On October 30th, Boilerplate 28, which was fitted with a flight article aft heat shield configuration, was tested to failure in the Downey pool. Instrumented dummies recorded simulated human reactions to the impact. The test represented the most severe conditions of impact, angle, and velocity under which a manned command module can land with only 2 parachutes operating. Failure of the ablative heat shield supporting structure pointed the way to design modifications which are presently being implemented. The level of subsystem development work was seen in the delivery of the first production guidance and navigation station by AC Sparkplug, Milwaukee. MIT's instrumentation laboratory is responsible for the subsystem design. The Honeywell Corporation, Minneapolis, Minnesota, conducted stabilization and control subsystem verification tests on a special air-bearing table. The device simulates the weight and inertial characteristics of the Apollo spacecraft. Rocketdyne continued development test firings of the command module reaction control engines at their Santa Susana field laboratory. 12 such 8-inch long RCS engines will be used on each command module. At East Hartford, Connecticut, Pratt & Whitney proceeded with dynamic tests of fuel cells for the command and service modules. During the summer months, the first service propulsion subsystem engine was erected at the Propulsion Systems Development Facility, MSC's White Sands operations. The engine is manufactured by Aerojet General, Sacramento. A breadboard service propulsion subsystem was used for the tests. The first firing took place in September. Over 20 additional test firings were conducted through the end of the year. The Service Propulsion Subsystems area is one of 4 major PSDF installations. Other facilities include an administration area, a test preparation area, and a Lunar Excursion Module engine test area, which is the only PSDF installation still under construction. It was 94% complete by the end of the year. In October, the Lunar Excursion Module was the subject of a mock-up review held at Grumman Aircraft, Bethpage, Long Island. This was the first metal mock-up, and it included complete interior and exterior systems arrangements. It was basically approved as the lunar landing configuration. The mock-up will be kept as an engineering tool and will be maintained to the current status of LEM design refinements. Work on the LEM descent engine proceeded at San Juan Capistrano, where Space Technology Laboratories is developing a mechanically throttled engine design. STL inaugurated their high-altitude test stand with a vacuum test of the engine on August 25th. The facility produces an engine nozzle vacuum approximating that of the lunar surface. LEM flight training came a step closer to reality with the rollout of a lunar landing research vehicle at NASA's Flight Research Center, Edwards Air Force Base, California. The first test flight took place on October 30th. Gross takeoff weight, including the pilot, is approximately 3,700 pounds. The LLRB is the first of 2 such craft to be delivered by Bell Aerosystems, Niagara Falls, New York. It is designed as a free flight vehicle to simulate the LEM's lunar landing and takeoff profiles and control requirements. Thus, by the end of 1964, the combined efforts of government and industry had made significant and orderly strides in all manned spacecraft programs. The stage was set for forthcoming Gemini launches and the resumption of manned space flights by the United States. The Apollo program entered a period of rigorous testing to certify the flight readiness of the first Apollo spacecraft and their subsystems. And progress on the Lunar Excursion Module forecasted increased activity as mock-up designs were approved for prototype hardware. The last 6 months of 1964 were marked by the completion of a growing number of significant milestones, each representing a building block, another major step forward in achieving the nation's manned spaceflight goals.